All right, geometry, we are on to the second section of this unit, and we're going to take our knowledge of circles and move it forward talking about chords and arcs. The standard that we're working on today identifies and describes the relationships among inscribed angles, radii, and chords. Remember, radii here is the plural of the word radius. So quick vocab review. Again, there's no notebook here in the corner, so you don't have to have it in your notes as long as you know what it means. A chord is a segment whose endpoints are on a circle. An arc is part of the circumference of a circle and is tied to a central angle. If you have a central angle that forms here when two radii meet, then you also have an arc that forms out on the circumference. Our first theorem is up here, and it has to do with two central angles, or central angles that are formed. If you have a circle or a set of congruent circles, and you have central angles which are congruent, for example, these two central angles are congruent, and we know that because they're vertical angles, and we remember from earlier in the book, earlier in the level, that vertical angles are congruent. So if we have this angle NCH is congruent to XCV, then we know that the corresponding arc length along the circumference of the circle is also congruent. So the opposite of that is also true, what we call the converse. If the arc lengths are congruent, then the central angles also must be congruent. So I like to put all of my theorems on tiny little note cards. It makes it easier for me to decide which ones to use. So you can see here that I took all of what was on that slide there and shortened it down to just those couple sentences. The measure of the angles, if you have two congruent central angles, then the measure of the arcs are congruent. And then the converse, that if you have two congruent arcs, then the central angles are congruent. So that's our first theorem for today. Next, we're going to talk about chords and central angles. So you'll notice I have those same two central angles that are formed here. And in the last theorem, we discussed how if the central angles are congruent, then this arc length here is also congruent. But in this one, you'll see within a circle or in congruent circles, congruent central angles also have congruent chords. So when we're looking at these pieces, we kind of have three different pieces that are going on here. The central angle, the arc length along the edge, and the chord length. What this theorem tells us is that if two of these are congruent, if the angles are the same, then all of them are congruent. That they produce congruent arc lengths and congruent chord lengths. Obviously, the converse of that is true. If you have congruent arc lengths or congruent chord lengths, then you have congruent central angles. So all of those go together as a package. I suppose you want to see that one too. So there's my little tiny card. And it shows there that my statement, if you have central angles that are congruent, then you also have congruent chords. And if you have congruent chords, then you have congruent central angles. So we're getting close to the end. There's probably two more left. So I just lost that one. Sorry, my card wandered off. The next theorem talks about chords and arcs also. Big surprise, chords and arcs the whole way through. And it tells us that if we have circles or congruent circles and we have congruent chords, that also means we have congruent arc lengths. So in this one, if we know that BE and CD, the segment, the chord there, are congruent, then that also tells us that this arc length here along the side, the arc length BE, is congruent to the arc length of CD. And again, the converse of that is true. If we have congruent arc lengths, then we have congruent chords. Now when we write that one out, I just want to make sure that you guys realize the difference between the symbol on the arc length and the symbol on the chord length. The arc length is arced, and the chord length is a straight segment line that you're used to seeing. So we can see right there that if we have congruent chord lengths, then we have congruent arc lengths, and if we have congruent arc lengths, then we have congruent chord lengths. They go together. So this brings us around to our last new theorem to talk about for this unit, and this has to do with equidistant chords. Excuse me. If inside of a circle you have chords, like this one, B, G, and D, C, that are equidistant from the center, right, then the chords are congruent. So notice on this one that AF is the same length as AE. And because of that, then, these two chords, DC, BG, are equidistant from the center, and thereby they have to be congruent. The converse of that is also true. It's a big lesson in converses this week. So if BG and DC are congruent to start with, the chords are congruent, then they are equidistant from the center. So congruent chord lengths, equidistant, or equidistant, congruent chord lengths. And I like to write that one down too. It doesn't look quite as fancy on my little note card, but notice it says that if the two are equidistant, so they're the same distance from that center, then the two chord lengths are equal, and then the converse, which is that if the chord lengths are equal, then they are equidistant from the center. So that was a long list of theorems in this unit. I think there's about 4 or 5 of them. I leave you with a geometry joke, and then in the next video I'll go through and work out some examples for you.